In pitch-black aquatic environments, visual input drops to zero. A predatory fish navigating a muddy river system or deep ocean trench hunts completely blind. The prevailing theory in the tackle industry suggests that catching these fish requires loud, rattling lures. The assumption is that disorganized acoustic noise is the ultimate trigger for a strike. This data map shows acoustic waves radiating from a single point. As they collide with suspended particulates, the waves scatter, losing signal strength. This energy dissolves into disorganized static. Without a distinct origin, the predator loses the spatial resolution required to pinpoint the lure's location. Relying on scattered acoustic noise presents a significant disadvantage. Precision hunters require a signal that maintains its geometric structure, even in debris-saturated water. Consider a silent, wide-wobbling lure instead of a noisemaker. It acts as a bluff body, a solid object moving with force against a highly resistant medium. In the absence of light and reliable sound, the physical displacement of the water itself provides a direct, trackable metric. As the silent lure carves aggressively through the dark, it physically shears the dense water. This resistance leaves distinct, swirling patterns tracing its exact path. In fluid dynamics, this highly structured wake generation is classified as vortex shedding. To trigger a blind strike, a transmitter must project a distinct physical hydrodynamic signature rather than chaotic acoustic noise. This physical trail forms a Kármán Vortex Street. It is a universal fluid dynamic phenomenon where alternating high and low pressure vortices shed from the back of a bluff body. This satellite photograph shows the universality of this physical law. Wind passing an island creates alternating spiral cloud patterns, stretching for miles across the ocean. This 2D visualization demonstrates the same geometry occurring underwater. The separation of shear layers behind the lure creates an alternating high and low pressure wake. Fluid dynamicists show these vortices form in a predictable sequence, strictly dictated by the object's velocity and diameter. The water medium does not scatter this physical signal. It organizes the displacement into a geometric path leading directly back to the target. To read this geometric path, the predator operates as a highly sensitive biological pressure transducer. Stretching along the predator's flanks is the lateral line system, a network of subdermal, fluid-filled canals. This schematic of a lateral line canal isolates a single neuromast. Inside, modified hair cells physically bend in direct response to shifting external pressure gradients. This mechanical bending is instantly transduced into electrical neural signals, traveling straight to the fish's brain. The predator does not hear its target. It physically feels and decodes the precise geometry of the vortex street in real time. By processing these incoming pressure gradients, the predator's neural network calculates the size, speed, and trajectory of the lure without visual confirmation. This geometric overlay illustrates the Karman gate. To intercept the target, the fish phase locks its body movements to the alternating frequencies of the vortex street. This allows the predator to move with minimal metabolic effort, using the vortice's energy to hold its position. The result is a calculated strike. The blind predator intercepts the silent lure with precision in absolute darkness. The biological intercept demonstrates that in close-quarters hunting, decoding physical pressure provides a level of spatial accuracy that acoustic sensing alone cannot match. Contrast the elegance of the biological lateral line with traditional acoustic tracking hardware, which relies on bulky arrays of dials, thick wiring, and blunt acoustics. Modern engineers face significant hurdles when navigating autonomous underwater vehicles. In dark, zero-visibility environments, radio frequency and GPS signals are rapidly attenuated by the water. To solve this, researchers are currently reverse engineering fish biology to create the artificial lateral line. This comparison shows how micro-electromechanical systems, or MEMS, are mounted on submarine hulls to replicate the pressure sensing capabilities of biological neuromasks. Operating in zero-visibility environments isn't about the volume of the signal, it is about the precision of the hydrodynamic signature.